Here is a combined summary of the two pages. Group Activity Recognition (GAR) aims to classify collective activities from videos, which is essential for video understanding and has various applications. Existing RGB-based methods encounter challenges such as background variations, occlusions, and significant computational overhead. They typically employ CNN backbones to extract individual features and model interactions using RNNs, GNNs, or transformers. However, these methods have limitations, including reducing batch size or employing frame sampling to manage high computational and memory demands. To overcome these limitations, the authors propose a novel approach using a panoramic graph that incorporates multi-person skeletons and objects to encapsulate group activity. This graph enables Graph Convolutional Network (GCN) to unify intra-person, inter-person, and person-object interactive modeling through spatial-temporal graph convolutions. The authors develop a pipeline that extracts skeleton coordinates using pose estimation and tracking algorithms and employs Multi-person Panoramic GCN (MP-GCN) to predict group activities. The panoramic graph represents a group activity as a collection of multi-person skeletons and object keypoints, as shown in Figure 1. This approach leverages the strong prior of the skeletal graph, which enhances the feature extraction capabilities of spatial and temporal graph convolutions. The authors argue that existing skeleton-based methods lack effective structural prior for the relationships of keypoints, requiring relational reasoning or specialized hierarchical models. The proposed MP-GCN method achieves state-of-the-art performance in both accuracy and efficiency on volleyball and NBA datasets, outperforming RGB-based approaches by using only estimated 2D keypoints as input. This approach offers an effective alternative to RGB video, providing a lightweight and informative representation of human motions without requiring accurate individual annotations and specialized interaction reasoning modules. The paper presents a novel pipeline for skeleton-based group activity recognition, leveraging pre-trained pose estimation and object detection methods to extract keypoints for both humans and objects. A reassignment strategy coupled with pose tracking algorithms is developed to enhance consistent identity assignments across frames. The authors introduce a panoramic multi-person object graph that integrates the keypoints of multiple human skeletons and objects, overcoming the limitations of vanilla human skeleton representations. This graph unifies intra-person and inter-person interaction modeling, providing a comprehensive representation of group activities. The proposed method, MP-GCN, outperforms state-of-the-art keypoint-based methods on volleyball, NBA, and kinetics datasets with significantly lower computation cost compared to RGB-based methods. The paper also reviews related work in group activity recognition, including RGB-based methods, interaction modeling, and skeleton-based GAR. It highlights the challenges of video-based methods, such as computational resources and background variations, and the potential of using pose data as an alternative. The authors discuss various approaches to modeling interactions within group activities, including the use of graphs, RNNs, GCNs, and transformers. They emphasize the scalability issues of conventional GCN methods when applied to multi-person scenarios and the innovations of recent GCN-based methods in modeling interactive relations for recognition. In conclusion, the paper proposes a new pipeline for skeleton-based group activity recognition that leverages a panoramic multi-person object graph and MP-GCN. This approach addresses the shortcomings of previous methods, unifies intra-person and inter-person interaction modeling, and outperforms state-of-the-art keypoint-based methods with lower computation cost. This research paper proposes a novel approach to group activity recognition in videos, leveraging a multi-person object graph that integrates human and object information into a panoramic view. The authors address limitations in conventional skeleton representations by introducing an undirected graph G, which includes end joints and several bones to represent a person's body. They also incorporate object keypoints and connect them with human skeletons to form a human object graph. The paper discusses the use of graph convolution, particularly spatial graph convolution, SGC, and temporal convolution network, TCN, layers, to capture spatial relationships among skeleton joints within a single frame and temporal dependencies across multiple frames. The authors highlight the SGC operation, which applies a weight function to categorized neighbor nodes and uses a normalizing term to balance the influence of different subsets. The authors introduce a multi-person graph, viewing all individuals in a scene as a unified group. This graph is organized as a multi-person graph X with an adjacency matrix A, which captures intrabody connections for each individual and interbody relationships. The panoramic multi-person object graph integrates human object and multi-person graphs, providing a detailed and holistic representation of group activity. The architecture of MP-GCN is also presented, comprising basic blocks that include SGC layers and TCN layers. These layers are applied to extract information embedded in the multi-person object skeleton graph. The authors demonstrate how this approach can effectively recognize group activities by leveraging the spatial and temporal information from the panoramic graph. The paper presents a novel approach to group activity recognition, GAR, using a multi-person spatial graph convolutional network, MP-GCN. It leverages a panoramic graph to model both intraperson and interperson interactions within a singular graph convolution framework. The model architecture is designed with an early fusion strategy, incorporating 4 input branches for joint, bone, joint motion, and bone motion data. This approach significantly reduces complexity compared to conventional ensemble solutions. The basic block of the MP-GCN consists of a spatial graph convolution, SGC, multi-scaled temporal convolutional network, TCN, and spatial-temporal person attention block with module-wise residual links. The SGC operates on the entire panoramic graph, maintaining the graph scale throughout the network. The TCN captures temporal dynamics in consecutive frames using a 4-branch multi-scaled temporal convolution layer. The spatial-temporal person attention module computes attention scores for individuals across frames, enabling the MP-GCN to focus on key individuals and objects in crowded scenes. This module mitigates the impact of irrelevant roles and enhances the recognition of group activities. The paper also discusses a tracking-based pose reassignment strategy to enhance data consistency and filter out irrelevant individuals when preparing skeletal data. This strategy maps a variable number of individuals per frame to a fixed number using a read tracker and evaluates the activeness of each person based on their trajectory. The pose reassignment prioritizes individuals who are more likely to play a significant role in group activities and enhances temporal consistency of the obtained skeletal data. The research focuses on developing a skeleton-based graph attention network, GAR, for recognizing group activities in sports, leveraging panoramic graphs. It presents experiments on 2 datasets, Volleyball and NBA. For the Volleyball dataset, the authors report multi-class classification accuracy, MCA, for group activities and mean classification accuracy, IMCA, for individual actions. They utilize YOLOV8 for pose estimation and object detection, fine-tuning the model on a custom dataset for detecting basketballs and nets on the NBA dataset. The training and testing batch size is set to 16, with a warm-up strategy for the first 5 epochs. The learning rate decays according to a cosine scheduler after the 5th epoch. The authors compare their method with state-of-the-art approaches on both datasets, showcasing improved results in group activity recognition and individual action recognition. Here is the combined summary. The proposed MP-GCN method achieves state-of-the-art performance on the NBA dataset, outperforming video-based methods with significantly fewer parameters and lower computational costs. In the weakly supervised setting, the method still achieves satisfying results, demonstrating its compatibility with both high-quality and noisy keypoints data. A comparison with state-of-the-art methods on the NBA dataset is presented in Table 2, where the MP-GCN method outperforms others in MCA with fewer parameters and lower flops. The method's performance is further improved when late diffusion is adopted. An ablation study on graph structure is conducted, where different graph settings are experimented on the Volleyball dataset. The results, presented in Table 3, show that the proposed panoramic graph structure, which includes both intra- and interperson connections, achieves a significant improvement of about 1.5% in MCA with tolerable increases in parameters and flops. The effect of the number of graphs, M, is also investigated, and the results, presented in Table 4, demonstrate that m equals 12 obtains the highest accuracy, which is consistent with the typical composition of a basketball game. Additionally, the effect of object information is examined, and the results, presented in Table 5, show that incorporating object keypoints into the graph structure leads to significantly higher accuracy, and that placing object keypoints separately from the multi-person skeletons results in lower accuracy. The panoramic graph structure, which includes both intra- and interperson connections, is shown to be effective in capturing the relationships between people and objects in the scene. The results demonstrate the effectiveness and generalizability of the proposed panoramic graph, which can be applied to various graph-based human action recognition tasks. The research paper proposes a novel pipeline for skeleton-based group activity recognition, addressing limitations in traditional human skeleton representations. It incorporates human and object keypoints into a multi-person object skeleton graph using a panoramic graph convolutional network. The pipeline includes human and object keypoints estimation, tracking-based pose reassignment, and collective activity recognition. The authors demonstrate state-of-the-art performance on 3 datasets: volleyball, NBA, and kinetics. The TSNE visualization of the graph structures shows a clear separation of classes, indicating the effectiveness of the proposed method. The comparison with other skeleton-based methods on the Kinetics 400 dataset highlights the value of object information, suggesting potential for further improvement. While the performance falls short of SOTA video-based methods, this gap presents opportunities for future research focusing on enhancing multi-person and object representations in uncontrolled environments. Here is a combined summary of pages 15 and 16 of the research paper. The authors present a comprehensive review of existing literature on skeleton-based group activity recognition, GAR, via panoramic graph. They acknowledge the support of various grants and foundations that enabled their research. The references provided cover a wide range of topics, including robust associations, multi-pedestrian tracking, sum product networks for activity recognition, and cost-sensitive top-down, bottom-up inference for multi-scale activity recognition. The authors cite works on convolutional relational machine for group activity recognition, social scene understanding, and end-to-end multi-person action localization. They also reference papers on real-time multi-person 2D pose estimation, channel-wise topology refinement, graph convolution for skeleton-based action recognition, and a unified framework for multi-target tracking and collective activity recognition. Further references include structure inference machines for analyzing relations in group activity recognition, skeleton-based action recognition in the wild, and revisiting skeleton-based action recognition. The authors also cite works on joint learning of social groups, individuals' actions, and subgroup activities in videos, as well as whole-body regional multi-person pose estimation and tracking in real time. Other cited papers focus on attention interactive graph convolutional network for skeleton-based human interaction recognition, actor transformers for group activity recognition, and unified keypoint-based action recognition frameworks. The authors also reference papers on dual-path actor interaction learning for group activity recognition, deep residual learning for image recognition, and progressive relation learning for group activity recognition. The review highlights the significance of hierarchical relational networks for group activity recognition and retrieval, as well as hierarchical deep temporal models for group activity recognition. The authors also cite papers on detector-free weakly supervised group activity recognition, skeleton-based action recognition of people handling objects, and social roles in hierarchical models for human activity recognition. Overall, the authors provide a thorough examination of the existing literature on skeleton-based GAR via panoramic graph, covering a broad range of topics and approaches in the field. This section of the paper provides an extensive review of various techniques and models used in group activity recognition, focusing on the role of skeleton-based graph attention networks. It begins by discussing the importance of understanding human interactions and group activities, which is crucial for applications such as surveillance, healthcare, and social media analysis. The authors highlight the challenges associated with group activity recognition, including the complexity of human interactions, variations in group size, and the need for robustness against occlusions and pose ambiguities. They also discuss the benefits of using graph-based models, which can effectively capture relationships between individuals within a group. A comprehensive overview of existing approaches is presented, covering both traditional computer vision methods and deep learning techniques. This includes the use of spatial-temporal graphs, graph convolutional networks, and transformers for modeling human interactions and recognizing group activities. The paper also reviews several datasets commonly used for evaluating group activity recognition models, such as the NTU RGB plus D120 dataset and the Microsoft COCO dataset. These datasets provide diverse scenarios and challenges that help researchers assess the performance of their models. In addition, the authors discuss various evaluation metrics and protocols used in this field, emphasizing the importance of choosing appropriate metrics that reflect real-world scenarios and challenges. Overall, this section provides a thorough examination of the state-of-the-art in group activity recognition, highlighting both the achievements and limitations of current approaches. It serves as a foundation for further research aimed at developing more accurate and robust models capable of handling complex human interactions in various environments. The supplementary material provides additional details on the keypoint acquisition process, including pose estimation and tracking, for the volleyball weekly supervised and NBA datasets. It utilizes the pre-trained Yueran 8x pose model to estimate human skeletons, following the official implementation of Yueran 8x. The Yueran 8x pose model conforms to the COCO keypoint layout, representing a person with 17 keypoints. For pose tracking, it integrates the BO TSORT tracker with default YOLO tracker settings. The visualization of the skeletal data used in the experiments is presented in Figure 1. It shows the extracted skeletons from the NBA dataset during instances of high-speed camera movement, as well as the results of extracting skeletons without using the ground truth individual detection for the volleyball weekly supervised and fully supervised datasets. The distribution of the number of individuals extracted in each frame from the volleyball and NBA datasets is illustrated in Figures 2a and 2b, revealing that the number of individuals frequently exceeds 20 in many frames. This underscores the necessity of adopting a reassignment strategy to accurately track important individuals across frames. For the NBA dataset, the keypoints of basketball and basketball net are extracted using the YOLOV8X model, fine-tuned for 50 epochs on a custom dataset. The number of basketball nets and basketballs detected in each frame is presented in Figures 2e and 2f, showing that basketballs and basketball nets are detected in approximately 75% and 90% of the frames, respectively. A comparison of the flops for RGB backbones used by prior works and YOLOV 8X is provided in Table 1. The results indicate that YOLOV 8X is more efficient than backbones such as VGG16 and VGG19. This is particularly relevant for the task of skeleton-based action recognition, which only uses an off-the-shelf pose estimation model. The research paper discusses the development of a skeleton-based GAR system using a panoramic graph. It highlights the distribution of individuals in frames from volleyball and NBA datasets, demonstrating the efficiency of the proposed reassignment strategy for tracking issues. The strategy improves the average track length per clip, enhancing the accuracy by approximately 1.3% compared to selecting by maximum confidence. The system's performance is evaluated using various input features, including joint coordinates, bone vectors, joint motion features, and bone motion features. The results indicate a marked improvement in performance when combining the reassignment strategy with a tracking algorithm. The study contributes to the field of skeleton-based human action recognition, emphasizing the importance of efficient tracking for accurate action recognition. The research paper discusses a novel approach to skeleton-based action recognition using a panoramic graph. It presents a detailed comparison with state-of-the-art methods on the volleyball and NBA datasets. The authors introduce a multi-person graph structure that leverages both joint and bone features, along with motion features between consecutive frames. This structure is fed into 4 separate input branches. The paper highlights the effectiveness of their method, achieving higher accuracy than other keypoint-based methods, especially when incorporating object keypoints. Additionally, it compares favorably with GCNs in skeleton-based human action recognition, showcasing the versatility of the proposed approach. The authors emphasize the importance of their method's multi-person graph structure and the incorporation of motion features in achieving superior performance. The paper discusses a novel approach to group activity recognition, leveraging a panoramic graph structure to model complex interactions between individuals in a group. This method is applied to both fully supervised and weakly supervised datasets, with the latter lacking ground truth detection boxes. The authors present a comprehensive analysis of their results, including confusion matrices and TSNE visualization for different graph structures. In the fully supervised setting, the proposed method achieves the highest performance on both datasets, outperforming baseline models and demonstrating the effectiveness of the panoramic graph structure in capturing group activity. However, when applied to weakly supervised datasets, the overall accuracy decreases due to missed detection and inaccurate tracking of key actors. The paper also presents additional qualitative results, including an exploration of various interbody graph topologies and their impact on recognition capabilities. The authors experiment with several connection strategies, such as fully connected, linear, and pairwise connections, finding that the pairwise connection strategy achieves higher accuracy and brings a more stable training process. Furthermore, the authors provide ablation studies on network modules, illustrating the significant contributions of each component to the model's recognition capabilities. They demonstrate that each module within the basic block plays a crucial role in enhancing performance, further solidifying the efficacy of their proposed approach. Overall, this research presents a groundbreaking method for group activity recognition, utilizing a panoramic graph structure to capture complex interactions and achieve state-of-the-art performance on various datasets. The comprehensive analysis and additional qualitative results underscore the potential of this approach for future research in computer vision and machine learning. Here is a combined summary of pages 27 and 28. The authors explore the effectiveness of various network modules and interbody links in a skeleton-based graph attention network for action recognition. Table 5 presents a comparison of different network modules in terms of mean class accuracy, MCA, on the Volleyball and NBA datasets. The results show that the combination of input branch, joint momentum, and body momentum, J plus B plus JM plus BM, yields the highest MCA, outperforming other module configurations. The authors also investigate the impact of different interbody links on MCA in Table 6. The pairwise interbody link approach is found to achieve the highest MCA of 95.54% on the volleyball dataset, surpassing other link methods, including fully connected and linear links. Furthermore, the authors examine the effect of input dimensionality on MCA in Table 7. The results demonstrate that incorporating visibility information into the input data improves MCA by over 1% for both two-dimensional and three-dimensional input data on the NBA dataset. Specifically, the addition of visibility evaluation to the three-dimensional input, X, Y, V, yields an MCA of 75.96%, outperforming the two-dimensional input, X, Y, with a visibility evaluation MCA of 74.48%. These findings highlight the importance of carefully designing network modules and interbody links to leverage skeleton-based graph attention networks for action recognition tasks. The results also underscore the significance of incorporating visibility information into the input data to enhance model performance.